1.5, and we are going to look at finding an inverse, an inverse function analytically. And so in the last lecture, I kind of showed we just plotted some points. We had a linear function. We plotted we switched the x and y coordinates, and then we plotted them, and then found another equation of a line that was in fact the inverse function. But we can't always do that. And so we need a way to do this algebraically. So we're just going to start with y equals x squared. Okay, so one way to find a function or an inverse for a function is to essentially switch the x and y, just rewrite them like the y becomes x and the x becomes y, and then solve for y again, and then that is the inverse. Okay, so let's just try this out for a second. This is going to demonstrate something that we need here. So I'm going to write x equals y squared, okay? And then I'm going to solve for y. So basically all I need to do is take the square root of both sides. When I do that, I put the plus and minus here. So I end up with y is equal to plus and minus the square root of x. Now we have recently talked about how we graph these functions. And so my inverse is kind of odd. I've got both a plus and a minus the square root of x. So if I go to graph that, right, this is the square root of x, and then the negative square root of x is this graph reflected down here. So what is my problem with my inverse? Oh wait, it's not a function. Okay, so we have a new test essentially. So everything that you can come up with, basically we can figure out some version of an inverse. But we in here want our inverses to be functions. So when we find the inverse, it is also a function because we prefer to work with functions. And so we have a new test, and we call this, so we have a vertical line test to show that something is a function, and now we have the horizontal line test, HLT for short, is basically a function f has an inverse function if and only if no horizontal line intersects with a graph of f at more than one point. Okay, so this is what the problem is up here, is that if I graph y equals x squared, right, this is a quadratic, and the horizontal line test tells me that my function will not have an inverse function unless it can pass this horizontal line test. So since I have a piece here and here, I end up with I end up with my inverse looking like this. Now there's ways that we can restrict the domain. Maybe I just decide I'm only going to work with this half of my quadratic, so I restrict the domain to x is greater than or equal to 0, so I can get around it. But as it stands with the domain, which is all real numbers, it does not have an inverse function. So you can kind of think of inverses, if you notice, they actually, if I graph, let me graph just this right half. So if I take this half of my graph, and I'm just going to basically say, okay, well, I'm just using x squared for x strictly greater than or equal to 0. Then the inverse is actually the positive piece here. And so if I graph these on the same graph, you can kind of see, now again, I'm not perfect here, but essentially a f and f inverse of x, they have this property where sort of if you think of this line that splits the first quadrant and it continues down here in the third quadrant, then inverses have this sort of reflective nature over it, because when I change the x and y coordinates, that's what ends up happening, is that I sort of get a reflection. It's not over x or y, right, or x or y, I guess this way. It's over the line y equals x. So you can kind of see if you sort of tilt your head to the right, and I kind of like do it like this, then on this line I have this reflective, like it looks about the same on both sides. So that's what happens. That's the way graphically inverses present each other. Okay. All right, so let's talk about how we find an inverse. Okay, so first, I said we switch the x and y's, but there's a little bit more to it than that. Okay, so the first thing that we need to do is we're going to use the horizontal line to find out if f has an inverse function. Okay, so we always want to deal with that first. Okay, then if f passes the horizontal line test, we interchange f of x with y. Usually our functions, right, are named, so we interchange their name, f of x, with the y coordinate. Then we switch x and y and solve for y. We did that on my first little mini example there. And then once we're solved for y, we replace y with f inverse of x in the new equation. That way we can tell what's the inverse. And then if we want to, we can verify by using composition of functions. Remember that we decided that the definition of an inverse would be as if I compose f with f inverse of x in both directions, it should be x. So if I have f inverse composed with f, this should also be x. So that's what makes them for sure inverses. All right, so let's use this. So let's use a nice simple example. So I have f of x is equal to x cubed minus 1. All right, so this is the graph of an x cubed function. An x cubed function, right? And I'm minus 1, so I can graph this really quickly, right? I'm not doing a complete graph here. I just want to know general picture. Will it pass the horizontal line test? So x cubed, right? It looks like this, right? And if I'm going to subtract, it's just my graph is shifted down 1. Okay, so this is just generally speaking, and it looks good to me, right? It looks like it's going to pass the horizontal line test here. So here's my x, here's my y. I should label it a little bit better than that. So I've just got the graph of x cubed, which is this general shape, and it's just shifted down 1 unit below the x-axis. So it passes the horizontal line test. So let's follow our steps. So if it passes, then what we do is replace f of x with y. So first step, there we go. Okay. So now what I'm going to do is my y will become x, and this x cubed will become y cubed. So I'm just essentially flip-flopping my variables. And we do this basically to be able to undo, right, what f does. All right, so now I want to solve for y. So again, here's my y. I'm going to add 1 to both sides, so I get x plus 1 equals y cubed. And then to get y alone, in my final step, I'm going to take the cube root of both sides. So I have cube root of x plus 1 is equal to y. And remember, I don't put plus and minus with the cube root, right? So this is y is equal to the cube root of x plus 1. My last step then is to just rewrite f inverse of x as the cube root of x plus 1. All right, so just a quick check. All right, I'm not going to formally do it here, but maybe I'll test one way to use the composition. So I can kind of see if I put f inverse, so if I put this inside of f, right, then I'm going to have, this is the cube root of this. So when I cube this, I'm going to just get this back. It'll be x plus 1. I subtract 1 and I'm going to get x. So if you need to write it out, that's fine. But I'm just kind of doing a quick check. So then if I take this and put it inside of f inverse, then I'm going to have the cube root of my new x becomes x cubed minus 1. So I get x cubed minus 1 plus 1, which is just x cubed. The cube root of x cubed then is x. So I've just quickly verified that I've done my algebra correctly. Okay, so this is f inverse of x. All right, so let's do this. All right, so let's look at another example here. I have y equals, let me use f of x actually. Let's use f of x equals x squared minus 1, and we're going to use x less than or equal to 0. Okay, so this is a quadratic, right? And it definitely isn't going to pass the horizontal line test without a domain restriction. But this one very kindly says, oh no, wait, we're just going to use x less than or equal to 0. All right. So if I think about what this looks like, x squared minus 1 would normally be a quadratic. It's just shifted down 1 unit. This is saying x is strictly less than or equal to 0. So that means my graph is on this side only. Right? This is just a quick sketch. So it looks like this. All right. So it does in fact pass the horizontal line test as long as I don't draw the other half, which I'm not supposed to because I have this domain restriction. All right. So it does have an inverse, so let's find it. Okay. So I have y equals x squared minus 1. I'm going to swap out my variables. X equals y squared minus 1. So I'm going to add 1 to both sides and get x plus 1 is equal to y squared. And then I take the square root of it. Now normally when I do this I put plus minus, but I'm going to put plus minus here for a second and know that both of these are not my inverse, okay? So I need to make a decision about which one it is, okay? And so this is the general rule of thumb. When I'm using the positive side of the x-axis, right? If I'm using this side of my quadratic or something that if I'm using the right-hand side, then I'm going to use the positive square root of x plus 1. But in this case, I'm using basically the negative values of x here. And that means I'm going to use my inverse, f inverse of x, is the negative square root of x plus 1. Right? So we already know how to graph this too. So if I put it on the same, I get something that looks like that. Okay. Oh, actually, I do not, right? I've not put my this is the positive version. I knew that wasn't right. Okay, so actually it looks like this, right? Without this part. So you can kind of see it, right? If I kind of split this in half. So that, right, that solidified my point that here I look like, if I looked at this, it doesn't look like a reflection over the line y equals x at all until I move it, right? So it's shifted back and then reflected down. All right, so let's do one that's a little bit more algebraically complicated. All right, so this time I'm not going to check. I'm just, because we haven't talked about rational functions yet, but this is a rational function. We're going to talk more in detail about them right now, but for right now, I'm going to tell you that this function does in fact pass the horizontal line test, and if you don't believe me, then you can go to Desmos.com and graph it, okay? And so I'm going to find the inverse of this. So I'm going to replace this with y equals 3x minus 2 over 4x plus 2. And I'm going to change my variables. So this one's a little bit more algebraically complicated. So I have x is equal to 3y minus 2 over 4y plus 2. Right, so I want, right, I can't solve for y while it's in the denominator, so I need a way to get it out. And so the way that I do that is to multiply both sides by my denominator. On this side, I get this lovely cancellation, which is what I wanted. So, and on this side, I get x times, I'm just going to write it in a different order, 4y plus 2 is equal to 3y minus 2. All right, so I have a y in my parentheses and a y on the other side. So what I need to do is open up my parentheses first and foremost. Okay, so let's distribute this x. So I get 4xy plus 2x equals 3y minus 2. All right, now I don't see any exponents here, right? So it's not like I have a quadratic or anything like that. But I can kind of see that I have an xy term here and I have a y term here. There's no way I'm going to be able to solve for y because I don't just divide out x on the left-hand side because x could be 0 and we don't just generally divide by the variable to get rid of it, right? Because that would eliminate it from the entire right side. So what I want to do instead is I'm going to get all the terms that have y on one side of the equation. I'm going to choose to move all my y's on this side. So anything that does not have a y, it's going to move to the other side. So this 4xy is fine over here. And I want this positive 3y to move to this side. So that means I'm going to subtract it from this side. It'll go away and end up over here as minus 3y. Now this 2x that's on this side already, I don't want this here because it doesn't have a y in it. So I'm going to subtract it, and I'll just put it over here, and then the minus 2 was fine there. Okay, so this 2 became negative 2 over here. This negative 3y came from this positive 3y on this side. So I've just traded these two, okay, and changed the signs of both. All right, so now, right, factor, right? I have a y here, and I can factor out the y. So I have 4x minus 3 equals negative 2x minus 2. And then in my last step, I just divide by this whole thing, right? If this were 3y, I would just divide by it. Now, of course, I can't use whatever x value I put in the denominator that makes it equal to 0, but that's a domain restriction on it. So this is our f inverse of x. All right. So we will talk more in depth in class.